Welcome to Mrs. Lee's Chemistry Academy. Today we're going to talk about Module 7 on the type of chemical bonds. This is related to the learning objective from College Board 2.17. Student can predict the type of bonding present between two atoms in a binary compound based on the position in the periodic table and the electronegativity of the elements. Able to work and justify the ranking of bond polarity on the basis of the locations of the bonded atoms in the periodic table. To explain a representation that connects properties of an ionic solid to the structural attributes and to the interactions present at the atomic level. And create or use graphical representations in order to connect the dependence of potential energy to the distance between atoms and factors such as bond order and polarity, which will influence the interaction strength. Bonds are strong electrostatic forces that hold groups of atoms together and make them function as a unit. Bonds form because the energy of the system is lower than if bonds did not form. Now here's a diagram showing the interaction between two hydrogen atoms. On the y-axis we have potential energy in kilojoule per mole, and on the x-axis we have internuclear distance in nanometers. Looking to the right-hand side, you have two hydrogen atoms being infinitely far apart from each other with no attraction, where the potential energy is zero. As the two hydrogen atoms come closer together, then they have some kind of attraction between the protons and the electrons. Finally, the energy will be lowered to a minimum, which is at negative 458 kilojoule per mole, and that's when it is in the most stable form, and that's when we define the bond length of the covalent bond to be 0.074 nanometers. Now, if they become closer than that, then there will be repulsion between the proton and protons and electrons, and these two hydrogen atoms will then go further apart, and then the potential energy will rise. The system minimizes proton-proton and electron-electron repulsions and maximizes proton-electron attraction to achieve the lowest possible energy. Bond length is the distance between the nuclei of two bonded atoms, where potential energy is at the minimum and attractive and repulsive forces are balanced. Whereas bond energy or bond enthalpy is the energy in kilojoule per mole required to break a bond. This is the net energy of stabilization of the bond compared to two separated atoms. When we compare the covalent bonds, we can look at the single bonds, which is formed by one shared pair of electrons, such as in hydrogen, fluorine, chlorine, bromine, and iodine, these diatomic molecules. A double bond is formed with two shared pair of electrons, meaning 4 electrons, in oxygen. A triple bond is formed by 3 shared pair of electrons in nitrogen. Generally, when we have more shared pair of electrons, the bond length will be shortened because then the atomic nuclei are joined closer together and the bond energy increases. Practice problem number 1. Rationalize the relative bond length and bond energy of hydrogen, oxygen, and nitrogen molecules. So you look at the numbers here. Looking at hydrogen, bond length is 74 picometer, bond energy 432 kilojoule per mole. Now when we move into oxygen, the bond length is longer, 121 picometer, bond energy also a little bit higher, 495 kilojoule per mole. Then when we go into nitrogen, this time bond length is a little bit shorter at 110 picometer, but the bond energy is very strong at 941 kilojoule per mole. Hydrogen would have a single bond and one energy shell, so each valence electron is attracted very closely to the nucleus of the other atom, making the bond length to be the shortest. With oxygen and nitrogen, they have 2 energy shells, so they have the electron shielding effect from the 1s2 electrons. Therefore, their bond lengths are longer than that of the hydrogen. Now, the triple bond in nitrogen is shorter and stronger than the double bond in oxygen because nitrogen has more electron pairs drawing the nuclei closer together. And that's why when you compare the bond length between oxygen and nitrogen, nitrogen is a little bit shorter, but the bond energy is much greater. Bond order is equal to the number of bonds divided by the number of atoms bonded to the central atom. This is a measure of the electron density in the bond. For covalent bonds between the same elements, when bond order increases, bond length decreases and the bond energy increases. Now, if you look at the carbon single bond, bond order is 1 because there's only one bond and divided by one bonding atom. Bond length is 154 picometer, bond energy 348 kilojoule per mole. Now when we move on to the carbon double bond carbon, the bond order is 2 bonds divided by one atom. So the bond order is 2, with a bond length a little bit shorter now, 134 picometer, but the bond energy is stronger at 615 kilojoule per mole. Then we move into the carbon triple bond carbon. Bond order is 3. Now bond order increases, but the bond length now decreases to 120 picometer, and bond energy is further increased to 812 kilojoule per mole. Bond types. First, ionic bond. It is formed between an atom that loses electrons easily, and it will react with an atom that has a high electron affinity. Typically, a metal will be reacting with a nonmetal, and it's resulting from the strong Coulombic interaction between oppositely charged ions, meaning the electrostatic force. Whereas a covalent bond formed when electrons are shared between the nuclei of 2 nonmetal atoms to form a molecule or polyatomic ion. Here's a table of electronegativity, meaning the ability of an atom in a molecule to attract the shared pair of electrons to itself, meaning the bond to itself. And when you look carefully across, we'll notice that it is increasing across the period, hydrogen being 2.1, and then lithium being 1.0, increasing to fluorine, the halogen being 4.0. Now it's increasing because there's greater effective nuclear charge, more protons across the period. But when you move down a family group, we notice that it's decreasing to francium 0.7, and the reason for the decreasing in electronegativity is because of increased electron shielding effect, because there are more energy shells, more core electrons. The relative electronegativity difference, which we call delta, and we can use a set of rules to find delta value by taking the difference between the electronegativities between 2 atoms that make the bond and then classify it as a specific bond. When delta is greater than 2.1, we call that an ionic bond. When it is between 0.5 and 1.6, that's called polar covalent bond. And when it is less than 0.5, then we call that nonpolar covalent bond. The difference between ionic and covalent bonding is not distinct, but rather a continuum. If the delta falls between 2.1 and 1.6, which is not in the chart itself, then we have to look at the bonding atoms. If a metal is involved, then it is an ionic bond, and if a nonmetal is involved, it is a covalent bond. Electronegativity is related to ionization energy, meaning how strongly an atom holds onto its electron, and electron affinity, meaning how strongly an atom attracts another electron. Please note that as electronegativity increases, ionization energy also increases, and electron affinity also increases. Practice problem number 2. Calculate the delta and order the bonds according to polarity from least covalent to most ionic. First of all, with sodium chloride, the calculated value is 2.1. That's clearly ionic. With the OH bond, delta is 1.4, polar covalent bond. With the carbon-hydrogen bond, delta is 0.4. We call that nonpolar covalent bond. HF bond, 1.9 being the delta polar covalent bond. Carbon-chlorine bond, delta being 0.5 polar covalent bond. Therefore, when we rank them, starting with the CH, then to the carbon-chlorine bond, then to the OH bond, and then onto the HF bond, and finally ending with ionic sodium chloride. In the polar covalent bond, atoms with higher electronegativity develops a partial negative charge represented by delta negative relative to the other atom with a partial positive charge represented by delta positive. When charges of equal magnitude but opposite in sign, Q plus and Q minus, are separated by distance r, a dipole is produced. A dipole moment is a quantitative measurement of the magnitude of a dipole, and it is drawn as an arrow starting from the partial positive atom, so with a positive tail pointing toward the negative atom. So for example, if you have the hydrogen fluoride molecule, the HN being relatively positive, so we draw the dipole arrow starting from that point pointing toward the fluorine atom, which is partially negative. Greater differences in the electronegativity will lead to greater partial charges and a greater bond dipole. Now, why do we care about bond dipole? Because we can actually use the bond polarity to deduce whether the molecule is polar or not, and then we can find the right kind of solvent to dissolve that molecule. In terms of polarity of molecule, when bond dipoles cancel out each other, the molecule is nonpolar, such as CO2, SO3, and CCl4, which I will illustrate later on in another slide. But if the center of positive and negative charge do not coincide, they're not in the same place, they don't cancel out one another, then you have a polar molecule such as water and ammonia. All right, looking at this diagram here, if you look at the CO2 molecule, which is linear with carbon in the center, and we're drawing two bond dipoles from carbon toward oxygen, the bond dipoles will cancel out each other, therefore CO2 is a nonpolar molecule. Now looking to the right, water, we're drawing two bond dipoles from hydrogen pointing toward the negative oxygen atoms. Clearly, these two bond dipoles do not cancel out one another, and you'll have different places for the center of negative and positive charge. The center of negative is on the oxygen atom. The center of positive is between two hydrogen atoms. Therefore, now we have a polar molecule in water. In SO3 molecule, the bond dipoles cancel out each other, nonpolar molecule. In ammonia, the bond dipoles are drawn from the H atoms toward the end, the more negative atom. Notice that these bond dipoles do not cancel out each other. The center of negative is on N atom. The center of positive is on that imaginary triangular base between the three H atoms. They don't cancel out each other. We have a polar molecule. And finally, in carbon tetrachloride, all the bond dipoles cancel out each other. We have a nonpolar molecule. Now let's turn to lattice energy in binary ionic compounds. Lattice energy is the energy released when an ionic solid is formed from the gaseous ions. For example, sodium ion in the gaseous state combining with chloride ion in the gaseous state to form crystal solid NaCl, the lattice energy is negative 788 kilojoule per mole, exothermic. Now, lattice energy is based on the Coulomb's law, which is directly proportional to Q1 and Q2, the charge of the ions, and inversely proportional to the distance between them. That means the larger charges and the smaller ions will tend to have stronger electrostatic force of attraction and therefore greater lattice energy. And the higher the lattice energy, the higher is the melting point of the solid because more heat is needed to break down these ionic bonds. Now the bond-Haber cycle is a summary of the key steps to show how solid sodium chloride are formed from the elements and the energy involved. First, we need to sublime this sodium metal into gaseous state by inputting energy endothermically 108 kilojoule per mole, energy of sublimation. Then this sodium atom in the gaseous state will be ionized by using first ionization energy of 498 kilojoule per mole to knock off an electron to become sodium plus 1 ion. Now this is bond breaking. We take half a mole of chlorine gas molecule and break it down into 1 mole of chlorine atom. The bond breaking energy is endothermic, 122 kilojoule per mole. Then the chlorine atom will attract the electron that's given off by the sodium atom to become chloride ion. This is called electron affinity, which is exothermic, negative 349 kilojoule per mole. Finally, there is electrostatic attraction between the positive sodium ion and the negative chloride ion to form the solid sodium chloride. This is lattice energy, negative 788 kilojoule per mole. Now, if we add up the 5 steps in terms of the species and the energy, you will get then 1 mole of sodium metal with half a mole of chlorine gas molecule to form 1 mole of sodium chloride solid. The enthalpy of formation is negative 409 kilojoule per mole. So here's an energy diagram to show. Now with step number 1, the green arrow meaning endothermic energy is positive, in which the sodium solid is sublimed into gas. And in step number 2, here we have bond breaking. Half a mole of chlorine is broken into 1 mole of chlorine atom. This is also endothermic. And then step number 3, and this is first ionization energy for the sodium atom to become sodium ion. And then step number 4 will be for the sodium ion and the chloride ion, which is gaining the electron. The chloride ion gaining the chlorine atom gaining the electron to become chloride ion. That's electron affinity, and that's negative. And then step number 5 is the lattice energy. And step number 6 is just the reverse of step number 5. And finally, step number 7 will be the net energy, enthalpy of formation. Sodium chloride, being an ionic solid, has a lattice structure. Now here's a diagram of the lattice structure, meaning a whole bunch of alternate positive, negative ions attracted onto one another. Each positive sodium ion is surrounded by 6 chloride ions, and each chloride ion is surrounded by 6 sodium positive ions in a regular lattice. Practice problem number 4. Let's calculate the lattice energy of calcium chloride. Okay, here let us look at sublimation. The calcium metal is sublimed into calcium gas. Enthalpy of sublimation 121 kilojoule per mole. Then you have the first and second ionization energy of calcium to form +1 and then +2 ion. Is first ionization energy 590 kilojoule per mole, second ionization energy 1145 kilojoule per mole. Then you have the bond breaking of 1 mole of chlorine atom being broken down into 2 moles of chlorine, 1 mole of chlorine molecule being broken down into 2 moles of chlorine atom. Bond breaking is 244 kilojoule per mole. Then you have the electron affinity, the chlorine atom, 2 moles of that attracting 2 moles of electron to become 2 moles of chloride ion, negative 349 kilojoule per mole. And finally, the electrostatic, the enthalpy of formation. This is the final step summary of all the enthalpy of formation, calcium ion and the 2 chloride ion to form calcium chloride being negative 795 kilojoule per mole. So in the calculation, we start with the enthalpy of formation on the left. To that, we add the energy of sublimation, and then first and second ionization energy, and then bond breaking, and then electron affinity. Then we are solving for lattice energy, which turns out to be negative 2197 kilojoule per mole. Practice problem number 5. The lattice energy of sodium fluoride and magnesium oxide are 910 and 3795 kilojoule per mole respectively. Account for the differences. Why such a big difference between the two? So if we look at sodium fluoride, the Q1, Q2 are positive and negative 1, whereas with magnesium oxide, Q1, Q2 is equal to positive 2 and negative 2, which are the charges of the ions. So magnesium oxide would have a greater lattice energy by about 4 times greater than that of sodium fluoride. And if you look at the comparison between the magnitude of Q1 and Q2, you would know why it is 4 times greater. Now let's rank by increasing lattice energy for lithium fluoride, sodium chloride, rubidium bromide, and magnesium sulfide, and then calcium telluride. If you look at rubidium bromide, sodium chloride, LiF, they have +1, -1 charges for Q1 and Q2. If you look at calcium telluride and magnesium sulfide, they have +2 and -2 charges. So also in terms of the size, in the cation, rubidium is bigger than sodium, bigger than lithium ion, and calcium ion is bigger than magnesium ion. For the anion, bromide is larger than chloride, larger than fluoride ion, and telluride is bigger than sulfide ions. Remember, smaller ions and higher charges would have greater lattice energy. Therefore, the ranking will be starting with rubidium bromide. The next bigger one will be sodium chloride, and then LiF, and then calcium telluride, and then magnesium sulfide. So to summarize what we have learned in this lesson, students have learned prediction of bond type and rank bond polarity based on position of bonding atoms in the periodic table or their electronegativity values. 2. We learned how to rationalize the relative bond length and bond energies of diatomic molecules such as hydrogen, nitrogen, and oxygen. 3. We used the Bond-Haber energy cycle to determine the enthalpy of formation of an ionic compound from its elements. And finally, using Coulomb's law to account for the trend of lattice energy of compounds. From the team of MLCA, we would like to thank you for watching and hope that we will meet again soon in the next video.